Hi everyone. So the main thing we're going to be talking about in this video is the graphs and equations of circles. But we'll see that in order to understand where the equation for a circle comes from, we have to talk about something called the distance formula. And actually, even to talk about the distance formula, we first need to talk about the Pythagorean theorem. So it's going to take us a little bit to get to the part about circles, but that will kind of be the main objective of this video. So you might notice that we're going kind of backwards in the book. So we're going back to section 1.9. So the reason that this section is not included in chapter 2 is because chapter 2 is all about functions. And if you think about what a circle looks like, the graph of a circle is not a function. And we'll talk about that a little bit later. But basically, if you think about what the picture of a circle looks like, it fails the vertical line test. So it's not a function. And so that's why it doesn't really fit into chapter 2. But the reason that we're talking about it now is that, I wanted to basically get comfortable with graphs before we brought up graphs of circles. So just kind of taking a brief pause to talk about circles, and then we'll get back to talking about functions in the next few videos. Okay, so as I said, in order to understand where the distance formula comes from, we first need to review the Pythagorean theorem. So the Pythagorean theorem is a formula. Basically, it's kind of a fact about right triangles. And I think most people should have learned this at some point, probably in high school, maybe in a geometry class or an early algebra class. And so the Pythagorean theorem tells us a relationship between the sides of a triangle. So it specifically tells us that, a right triangle. So what is a right triangle? A right triangle is a triangle that has one 90-degree angle. So notice how there's this kind of square symbol that represents the fact that it's a right angle. So this fact we're about to write down is only true for right triangles. Okay, so if we label the two perpendicular sides of the triangle, so the two sides that form the right triangle or the right angle, if we label those with A and B, and then we label this third side, the diagonal side, with C, then the Pythagorean theorem tells us that it's always going to be true that A squared plus B squared is going to be equal to C squared. So just to add a little bit of vocab here, just in case it comes up and we want to be able to use these words, when you have a right triangle, the two sides that are form the right angle, those are called the legs of the right triangle, and the the diagonal side is what's called the hypotenuse. I don't know that we'll really be using those words, but they're probably good ones to know. So that is the Pythagorean theorem. So I just wanted to show you briefly a video that can give you an idea for why the Pythagorean theorem is true, because I think Pythagorean theorem is one of those things that a lot of us just kind of take for granted. You've seen it all throughout math. But yeah, I just want to show you this quick video. So my partner, who actually he teaches at Shoreline Community College, he's been playing around with learning some animation. And he made this video showing a visual proof of the Pythagorean theorem. So I'm just going to play this and kind of talk through what's going on, and I'll also link this video below. So basically the idea is if you have a right triangle and the sides are A, B, and C, if you draw a square using the length of each side, well then the areas of those squares are going to be A squared, B squared, and C squared, right? And so now how can we kind of connect this to the Pythagorean theorem? Well, we need to show that this blue area, the area C squared, can be created from the green and the red areas put together, right? Because then A squared plus B squared would equal C squared. And so what you'll see in this video is basically that if you cut up this green square, the one representing B squared, in kind of a clever way and rearrange it together with the red square that's A squared, you can put them together and get an area that is equal to the blue square. And so you'll see that. And so now we can see that again, a squared is that red square, b squared is the green square, which we now rearranged into this funny shape. And when you add them together, you get this blue square, which is c squared. So just wanted to show that to you because I think it's it's nice to find these proofs where you don't need to do a whole bunch of algebra or anything, but you can actually just kind of look at a video or an image and kind of get some intuition into why a certain statement is true. So now we're going to talk about the distance formula, and we'll basically see that the distance formula, which you also may have learned at some point in your mathematical career, we'll see that the distance formula is basically just another kind of restatement of the Pythagorean theorem. So what is the purpose of the distance formula? Well, the distance formula is basically for finding the distance between 2 points. So let's just jump straight into an example. And I'm not going to tell you the formula right off the bat. We're first going to just see how we can use the Pythagorean theorem to find the distance between 2 points. And then we'll kind of adapt that into a formula. So let's say, for example, that we wanted to find the distance between 2 specific points. So we're going to do the points 1, 2, and 4, 6. So I'm going to start by just plotting those 2 points. So 1, 2 would be here. And then 4, 6 would be here. Okay, so once again, you might already remember what the distance formula looks like, but let's pretend for a second you don't. And let's think about how you could actually just use the Pythagorean theorem to find this distance. So I think it really comes down to first understanding what we mean by the word distance. So the distance between 2 points means if you kind of directly measure from one point to the other, which in some cases is going to be diagonal, right, like this. And so this here is the distance, this dotted line I just drew in. So how could we make use of the Pythagorean theorem to find the length of that line that I just drew? Well, we need a right triangle, right? In order to use Pythagorean theorem, you have to have a right triangle. And so if I just go straight down from the top point and straight over from the bottom point, they meet up at a right triangle or at a right angle. So this is a right triangle. And so we can just use the Pythagorean theorem. So I'm just going to label the side that we're trying to find with C, right? That's the hypotenuse. And then let's try to figure out what the lengths of these two legs are. So the length of the horizontal portion of this right triangle, well, we can just kind of count, right? We can see that it has 3 units. It's 3 units long. And so this side has a length of 3. And then the vertical side, well, if we count those boxes, we can see that that has a length of 4. And so to find the length of C, we can just apply the Pythagorean theorem. So we can say 3 squared plus 4 squared is equal to C squared. And so that gives us 9 plus 16 is equal to C squared. So 25 is equal to C squared. And technically, if you were just solving this equation, 25 is equal to C squared without any context, like just algebra problem, then the answer would be either positive or negative 5, right? Because either positive or negative 5, when you square it, gives you 25. However, in the context of geometry, we're talking about a distance, a length of a side of a triangle, it's going to be a positive result. So we can just say that C is equal to positive 5. Okay. So that's how you can just use the Pythagorean theorem. But I want to kind of connect this, or I want to think of like another way to kind of come up with these two sides on the triangle that will then help us to adapt this into the distance formula. So where does this 3 come from, right? We found this 3 by just counting boxes, right? We just said 1, 2, 3. But without counting boxes, how could you use the points that we were given to find this length of 3? Well, notice that 3 comes from if you take the x-coordinate of 4 and the x-coordinate of 1 and subtract them, that gives you 3. Right? And so why does that make sense? Like, why would you be subtracting the x-coordinates? Well, if you're looking for the horizontal distance between the 2 points, and that's really what this is, right? Like, we're kind of, by drawing this triangle, we're kind of breaking down the distance into a horizontal part and a vertical part. It's like, how far do you have to go horizontally? How far do you have to go vertically? And to figure out how far you have to go horizontally, that's really just looking at what's the difference in the x-coordinates. And so I'm just going to write that down. That's the difference in the x-coordinates of the 2 points that we're trying to find the distance between. And when I say difference, well, difference in terms of math usually refers to subtraction, right? So 4 minus 1 would be the difference, and that gives us 3, which is the length we found. And then similarly, this 4, we can think of this as being the difference in the y-coordinates, right? This is saying, like, vertically, how far do you have to go from 2 to 6? And so 6 minus 2, that would be how you'd calculate the difference between those 2 numbers. That's where the 4 comes from. Okay, so we're going to use the same idea now to kind of just like write down a general case. So I'm just going to sketch, I'm just going to plot 2 points here, and I'm going to actually not even give them like nice integer numbers because we want this to just refer to some like general case. So these are just 2 random points, and the way I'm going to label them is I'm going to label the first one with x1, y1. So that's just a generic way of saying we have some x coordinate, we have some y coordinate. And the 1 is to refer to the fact that it's the first point. And then similarly, I'll label the second point with x2, y2. So again, just saying we have some x coordinate, some y coordinate. And so we're trying to find the distance between those 2 points. So if we kind of just like replicate what we did above, and again, now we don't have numbers, we can't really count boxes, but we can still kind of use the same reasoning that we used above. And so how do you find this horizontal side? Well, what we did above was we subtracted the 2 x coordinates, right? And that found us the horizontal distance. And so this would be x2 minus x1, the horizontal change in between the 2 points. And then similarly, this side would have a length of y2 minus y1 because you would be calculating the difference in the y coordinates of the 2 points to see the vertical distance. And then to find the actual distance that we're looking for, instead of calling this c, I'm going to call it now d, right? Because d for distance. And so how could you find this length d using the Pythagorean theorem? Well, you would just say d squared is equal to, and so the horizontal side of this triangle would be x2 minus x1 squared plus, and then the vertical side would be y2 minus y1 squared. And so what happens if we solve this for d, right? We want to have, so the whole point of the distance formula is to have a nice, easy formula that tells you the distance between 2 points. And so really we want to take this equation that we currently have and solve it for d. And so the way that we can do that is by taking the square root of both sides. So we get d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And let me just draw the square root symbol a little better. And that is the distance formula. So specifically, let me kind of write this down in words. This is the distance between 2 points where those points are x1, x2, x1, y1, my bad, and x2, y2. So this is the distance formula. So rather than think of this as, a bunch of symbols that you have to memorize, I'd really encourage you to relate it in your mind to the Pythagorean theorem and try to remember it in that context. I think you'll have a lot of an easier time remembering it because there's a lot going on here, right? Like, how are you going to remember that this is supposed to be subtraction, but this is supposed to be addition? Well, it's because of where this comes from, right? So why is there subtraction going on here? It's because in this part here, you're subtracting the x coordinates to find a horizontal distance, a horizontal side of a triangle. Why are you subtracting here? Well, it's because you're finding a vertical distance. You're subtracting the y coordinates. Why are you adding here? Well, that comes from the Pythagorean theorem, right? The Pythagorean theorem says a squared plus b squared is equal to c squared. And so this is our, plus between those things getting squared. Why are you taking the square root? Well, it's basically just because we took this original Pythagorean theorem and solved it for d instead of having it in terms of d squared. So there's a reason for every part of this formula. One other just quick tip I want to give is that personally, I have a lot of an easier time memorizing a formula if instead of trying to memorize it as a bunch of symbols, I kind of memorize it as like a sentence in my head. So I like to think of this as, instead of d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared, I think of it as to find the distance between 2 points, subtract their x coordinates and square it, subtract their y coordinates and square it, add those two up and take the square root. So that might be something that you'll find helpful for remembering formulas, and that's something I'll probably emphasize in this class whenever we talk about a formula. All right, let's do one quick example of actually applying this, and then we'll move on to see how this is related to circles. So let's say we wanted to find the distance between 2 points. So the points are going to be 1, -2, and -3, 4. So main difference in this one compared to the last examples we did is that the points are negative, right? In both of the examples that we looked at, this specific one and then this one with just kind of like general x and y, everything looked like it was positive, right? So now we have negative coordinates, but we'll see it still works. So I actually first want to, without drawing the picture, just apply the distance formula, just so you can see that you don't need to draw a picture if you know the distance formula. You can just kind of plug the points in essentially. But then I want to show you what the picture looks like because it is a little bit different because of these negatives. So how do you find the distance? Well, you do the square root of, and then we're going to subtract the x coordinates. So that would be 1 minus -3. So make sure you're careful about parentheses here. If you're subtracting a negative, that's going to become plus, right? So you need to make sure that that actually happens. And then here to subtract the y coordinates, we do -2 minus 4. Okay, so let's see what this gives us. So we get d is equal to the square root of, so 1 minus -3, that becomes +4 squared. And then -2 minus 4 becomes -6 squared. And so that gives us d is equal to the square root of 16 plus 36. And so that gives us d is equal to, square root of 52. And so square root of 52 is not a perfect square. We can actually break this down a little bit. So this is something that we'll talk a little bit more about later in the class. I don't want to really make a big deal about it, but I'm thinking probably most of you have seen this. If you took like Math 98 at North, you should have learned this, that when you have a square root, you can break it down. So square root of 52, well, 52 is 2 times 26, which is the same as 4 times 13. So we can rewrite this as square root of 4 times the square root of 13, and that can be simplified as 2 root 13. So it's just a way of kind of simplifying a square root. Okay, so that is our distance. So let's draw these actual points and just try to make sense of what happened here because it's a little bit different. So we had the point 1, -2, so that's here. And then we had the point -3, 4, that's up here. Okay, and we're finding this distance here. So in this case, if we kind of draw in this triangle, so let's look at what we came up with in our formula here. Notice that the first part, we had 1 minus -3, and that gave us 4. And so 4, it turns out, is this correct distance here, right? Now, what's a little bit funny is that for the vertical part right here, oops, let me use a different color, we did -2 minus 4, which gave us -6. And that doesn't really make sense for the side length of a triangle, right? Really, if you count the boxes, this side actually has length 6, not -6. However, that doesn't really matter. So that's kind of my point in showing this to you, is that it doesn't matter whether you get a positive or negative result when you subtract, because you're going to end up squaring it, right? So technically, what we got here, -6, that's not the same as the side length. But because it's just the negative of it, it doesn't matter, because the whole, if you look at how the distance formula works, you're squaring it. So my point here is that basically that it doesn't matter which order you subtract your two numbers in. So let me just kind of show you something to emphasize that. So let's say that instead of doing, so notice how we did this, we did these points minus these points, right? We did 1 minus -3, and we did -2 minus 4. Let's say instead we had written the first part as -3 minus 1 squared, and then the second part we did 4 minus -2. So what would have happened then? Well, then for the first one we would get -4, but -4 squared is the same as 4 squared. You would still get 16. And then over here, we would get 4 minus -2, that's +6. So we'd get +6 squared instead of -6 squared, but +6 squared is still 36. So my point is that it doesn't matter what order you subtract the points in. It doesn't matter whether you get a negative when you subtract them, because you're squaring it. So you can just kind of trust that it will always work out. It doesn't matter what order you subtract them. It doesn't matter if you draw your picture and you're like, wait, why did I get a negative? It should be positive. Because everything's getting squared, that part just doesn't really matter. Okay, so now let's move on to talk about circles, and we'll see how circles are related to the distance formula. Okay, so my first question for you is, what is a circle? Like, if you had to explain to someone what does a circle look like, or what's the definition of a circle, what would you say? So, I'd imagine there's a lot of different things you could say. You could say it's a round shape, right? It's I don't know, it's hard to think. It's such a basic shape in, that we're so familiar with. But the technical mathematical definition that we're going to be working with is that a circle, and I'll explain why this is a good definition in a second. So a circle is the set, is the set of all points that are a particular distance, and that distance is called the radius, from a particular point. And that particular point is called the center of the circle. Okay, so why is this a good definition? Why is this the definition of a circle? Well, I would think about, one way that you could draw a circle would be, let's say that you have a string and a thumbtack. And so what you do is you take your thumbtack and you stick it through the string. And so you have this piece of string that has a specific length. And then let's say you have a pencil or a pen, and you kind of like go around and see how you can go all the way around in a circle with, keeping that piece of string taut. The shape you would get would be a circle, right? Because if you just think about it, like if you're always maintaining that same distance from that center point, you're just going to get a circle. That's just how circles work. And so the distance or the length of that piece of string would be what's called the radius of the circle. So that's when we say a particular distance called the radius. In this kind of string and pen analogy, that would be the length of the string. And then when we say from a particular point, well, that would be the thumbtack, right? That's the place where you're kind of starting your distance from. Okay, so I'm going to draw an example of a circle. And then what we're going to do is basically take this description that we have written down in purple, and we're going to translate that into a more like mathematical statement. Okay, so I'm going to draw an example of a circle. This one is going to have a center of the point 1, 2, and it's going to have a radius of 4. So radius of 4 means that every point on the circle, it has to be a distance of 4 from the center. And so I'm just going to do like 4 easy points to get started in graphing it. Okay. Not the roundest circle you've ever seen, but it's probably okay. So every single direction that you measure from the center to the edge of the circle should always have a distance of 4. So, for example, it's pretty easy to see that this is a distance of 4, right? But if I'd drawn this correctly, which I didn't quite, it looks a little bit smushed, then this distance would also be 4. This distance would also be 4. This distance, no matter where you go and draw it, the distance is always 4. Okay, so one other thing I just want to emphasize is that when we're talking about a circle, like the graph of a circle, we're actually only talking really about the part that I drew in black. So you might think of a circle and think of like this, the whole thing shaded in as being the circle. In this class, when we talk about a circle, we're just talking about the outside. So the points that are part of this graph are just all the points that lie all along the outside. We might draw the center because it's kind of an important reference point, but the center is not actually a point on the circle. When we're talking about points on the circle, we're always talking about, going back to that pencil and thumbtack analogy, we're talking about the points that the pencil would draw. Those are the points that are actually considered on the circle. Okay, so I'm just gonna label this point here X, Y, and you can tell, in this example, what the coordinates are of this point, but I'm just saying this is just any point X, Y, because I could have drawn the radius somewhere else, right? And X, Y just refers to any point on the circle. Okay, so the first thing I want to do is take this sentence or this definition that we have written in purple and kind of rewrite it a slightly different way. So if the circle is the set of all points that are a particular distance called the radius from a particular point called the center, well, in this case, the center is 1, 2, the radius is 4. And so what that means is that the distance from any point X, Y on the circle to the point 1, 2 is 4. So where did that come from? Well, it just came from what's written in purple, and then the fact that the center in this case is 1, 2, and the radius is 4, right? So any point you pick on the circle, whether it's, here or here or here or here or here, any point you pick on the circle, it's always going to be a distance of 4 from the point 1, 2. So how can we go and translate this into like a mathematical equation? Well, we just learned how to take distances, right? We now know how to write down the distance from a point to another point. And so in this case, what are our points? Well, one of the points is just x, y, and the other one is 1, 2. So let's write down what that would look like with the distance formula. So the distance formula, you take the square root of, and then you subtract your x coordinates. So that would be x minus 1 squared. And then you subtract your y coordinates. So that would be y minus 2 squared. So far we have basically addressed the part that I underlined in orange, right? This is the distance from xy to 1, 2 is exactly what I have circled in orange here. And then how do we write is 4? Well, we can just write equals 4, right? So this part is translated into equals 4. So we're pretty much done. Now, just to make this equation a little bit nicer, let's square both sides to get rid of the square root. So the equation of this circle would be x minus 1 squared plus y minus 2 squared is equal to 16, because I took the equation and I just squared both sides. So this is the equation of the circle. So I'll explain what I mean a little bit more when I say the equation of the circle in just a moment. But first, I just want to kind of decipher like where the different parts of this equation came from. So for example, like why is this minus 1? Where did this minus 1 come from? Well, the subtraction, we notice that both of them are subtracting, and that came from the distance formula, right? The fact that in the distance formula, you subtract the x coordinates, subtract the y coordinates. And then where did the 1 come from? Well, 1 was the x coordinate of the center, right? That 1 is there because 1 is the x coordinate of the center. And where does this 2 come from? Well, that comes from being the y coordinate of the center. So notice that, and this is going to be true for any circle, when you're writing down the equation of a circle, you're always going to be taking the x coordinate of the center and subtracting it from x, and taking the y coordinate of the center and subtracting it from y. And then where does this 16 come from? Well, it's not just the radius, it's the radius squared, right? Because originally the right side was the radius. If we go back to this 4 that I circled in green, because that was that distance, right? That's what that 4 represents, is the distance from the center to a point on the circle. But now we squared it, and so now it's 16. So we'll write down in just a second like what the general kind of format for the equation of a circle is, but I just want to quickly make sure that everyone understands what I mean when I say this is the equation of the circle. So this goes back to what we talked about with functions, because even though this graph is not a function, right? It's not a function because if you tried to draw a vertical line, it would fail the vertical line test, right? A vertical line would cross through this graph more than once, so it's not a function. But what we talked about in terms of the relationship between equations and graphs of functions, that is still applicable here. So remember that the relationship between the graph of a function and the equation of a function is that any point that lies on the graph, if you plug it into the equation, you should get a true statement, right? That's how you can always check whether an equation matches a graph, is take a point from the graph, plug it into the equation, and see whether you get a true statement or not. That's like a very, very, very important fact to know in this class, is that relationship between graph and equation. So one way that we could check whether this is the correct equation is we can test a point that we know lies on the circle and plug it into this equation. So, what's a point that we know lies on the circle? Well, actually this point 1, 6, right? This point here is a point that we can clearly see lies on the circle. So let's see what happens if we plug that point into our equation. If this is the correct equation, then we should get a true statement. So let's plug the point 1, 6 into the equation. And why are we plugging in the point 1, 6? Well, we're plugging that in because we know this lies on the circle. We can see from our graph that this is a point that lies on the circle. So if we go and we plug in 1, 6, that would look like x. So we're plugging in, by the way, 1 for x and 6 for y, right? So instead of saying x minus 1, now we're saying 1 minus 1 squared. And then instead of saying y minus 2, we're plugging in 6 minus 2. Does that make sense? So we're just plugging in 1 for x, 6 for y. And what we're testing here is, do we get 16? If this point is actually on the circle, then we should get 16. And so 1 minus 1 is 0, right? So we get 0 squared. And 6 minus 2 is 4, so we have 4 squared. So is 0 squared plus 4 squared equal to 16? Yes, it is, right? We get 16 on the left, we get 16 on the right. And so that's good. That means that, at least that's good evidence that our equation is correct. And you could also use this equation to check, like for example, if you wanted to check whether some random point lies on the circle, you could just plug it into this equation to do that check. Okay, so let's write down kind of a general fact here. So we just kind of came up with this for this last example, but now we can write it down in general. So if you're trying to write the equation of a circle, and if you know that that circle has a center of h comma k. So I don't really know what the reasoning for this is, but for whatever reason, the traditional letters that are used when you're talking about the center of a circle is h for the x coordinate of the center and y for the, and k for the y coordinate of the center. I don't really know why, but that's just how it is. And then if you know that the radius of the circle is r, then you're going to have the following equation for your circle. So let's just go back up to this previous example because it's basically just going to be this, right? So we did x minus the x coordinate of the center. We did y minus the y coordinate of the center. And then we had equals the radius squared. So that means that we're going to be doing x minus h, right? Because the letter h represents the x coordinate of the center. And then we have y minus k, because k is the letter that represents the y coordinate of the center of the circle, is equal to r squared. So my hope is that, by going through all of this stuff with the distance formula and everything, that you'll understand where this formula comes from. So that if you kind of forget it, you don't have to just rely on having it memorized. You can kind of trace back to this idea of, okay, I'm just finding the distance from a point on the circle to the center and setting it equal to whatever that radius is, right? Because the radius is supposed to be the distance. And then I'm just taking that equation and squaring both sides. And so that's why you have the radius squared on the right. That's why the square root goes away. But the x minus h and the y minus k, this part, these just come from the distance formula, right? That's really why you're doing x minus the x coordinate, y minus y coordinate, squaring them and adding them up, is because of the distance formula, which is also because of the Pythagorean theorem. It's really all the same idea. Okay, so let's get into a few examples of kind of like just making use of this formula. So first example I want to do is I want to write an equation of a circle. So we're going to write the equation of the circle. And by the way, I forgot to mention this earlier on, but as always, I really recommend, when we do these example problems, to pause the video and try them yourself. So I would say especially at this point. So let's try to write the equation of the circle that is centered at the point -2, 4, and has a radius of 11. So you don't have to sketch the graph, just come up with the equation. You can sketch it if you want, but. Okay, so how does this work? Well, we know that the formula for the equation of a circle is that you're supposed to do x minus the x coordinate of the center squared, and then you're supposed to do y minus the y coordinate of the center squared, and then that's going to be equal to the radius squared. And so what is the x coordinate of the center? Well, it's -2. So we have x minus -2. And then what is the y coordinate of the center? It's 4. And then on the right hand side, we're going to have 11 squared. Okay, so what does this simplify to? Well, if you're subtracting a negative, that's going to become just x plus 2. And so that's kind of a nice thing to recognize with circles, is that if the center is negative, has a negative x or y coordinate, you'll actually have plus. And that just comes from the fact that the initial formula has subtraction. So if you're subtracting a negative, that's how it becomes a positive. And then here we'll have just y minus 4 squared. And then here we'll have 121 is what you get if you do 11 squared. And so that is our equation. So one thing I just want to mention is that, you might be tempted to kind of like multiply these out, right? To do like x plus 2 times x plus 2. Don't do that. Just leave it in this format. There's nothing, I guess, really wrong with multiplying stuff out, but it would just make it a little bit harder to see what the center and the radius are. So the advantage of leaving your formula like this is that it makes it really easy to just look quickly at the equation and see what the center and the radius are. That's kind of the point of this format. Okay, next one, kind of similar, but this time, rather than being told what the center and the radius are, we're working with a picture. So we want to write the equation of the graphed circle. So this time we have to, for ourselves, figure out, what is the center and what is the radius. So what is the center? Well, we just kind of look at what looks like it's the central point in our circle, and it looks like it's the point -1, 3. So our center is -1, 3. So center, -1, 3. And then to find the radius, well, you could measure the radius any way you want. Like that's the radius, that's the radius, that's the radius. But if you're trying to figure out what the actual value of the radius is, it doesn't really make sense to measure it diagonally. You should measure it in one of the easy directions, right? So if we measure it downward, we can see, okay, that's a distance of 2. And so the radius is 2. Okay. So how do we write down this equation? Well, same as before, we're going to do x minus the x coordinate squared. So in this case, that's x minus -1 squared plus y minus the y coordinate, which is just 3 squared, is equal to, and then we take the radius and square that. So after some simplification, we end up with x plus 1 squared plus y minus 3 squared is equal to 4. All right, one last example. So this one, we're going to kind of go the other way. We're going to start with the equation and we're going to use the equation to draw the graph. So let me see, which equation do we want here? Okay, so we're going to sketch the graph of the following circle. So we're going to have x squared plus y plus 2 squared is equal to 9. So basically here we have to work backwards, right? We have to figure out what would the center be, what would the radius be, and then we can sketch it. So one thing that might be useful is to kind of rewrite the equation so that it looks a little more like this, right? To kind of rewrite it so that it's really clear what the center is and what the radius is. And so for this first part, we just have, sorry, that thing keeps popping up. So for the first part, we have just x squared, right? So it's, if it's x squared, what does that mean is that x coordinate we're subtracting? Well, 0, right? X squared is the same thing as x minus 0 squared. So basically, if you ever have just x squared or y squared on its own, that means that the x or y coordinate of the center is just 0. Now for this next part, we have a plus, right? And so remember that when you have a plus, that comes from subtracting a negative. And so if we want to rewrite this as y minus something, we have to rewrite it as y minus -2. And then for the right-hand side, if we want to see what the radius is, the radius isn't just going to be 9, right? Because the right-hand side is the radius squared. So we have to think of what number squared gives you 9. So we can rewrite 9 as 3 squared. Okay, so now this tells us our center and our radius. So our center is going to be the point 0, -2. And the radius is going to be the number 3. And so now we can go and sketch our graph. So we can go to the point 0, -2. So that's here. That's going to be our center of our circle. And then the radius is 3, so we can just count a distance of 3 in kind of the easy directions to count a distance of 3, and then do our best to connect it in something that looks like a circle. Oops. Okay, that's good enough. And I won't be super picky, on a test or a quiz or something if I'm asking you to graph a circle. As long as I can tell that you're trying to make it look like a circle, I'll be happy. I want to answer one more question about this graph. So what I want to ask you is, how could we figure out, does the point 5/2 -1 lie on the circle? So you could kind of look at the graph. So 5/2 would be like here, right? 2.5. And based on how I drew it, it kind of looks like that point does, but we also know that I didn't draw this circle great, right? That side kind of looks like it's smushed in. And I would just say it's a little bit hard to tell from, your own human sketch of a circle whether a specific point lies on it or not, aside from a few kind of easy points. So how can we know for sure? Well, we can test whether, we can test basically what happens if we plug this point into the equation. So what I'm going to do is just take the equation for the circle, and we're just going to plug this number in, or these numbers into the equation of the circle. So remember that the equation of the circle was x squared plus y plus 2 squared is equal to 9. So we need to see what happens when we plug in these numbers for x and y. So if we plug in 5/2 for x, that gives us 5/2 squared plus, and now we have -1 plus 2. So I'm just replacing x and y with with 5/2 and -1. And we're checking, does this give something that's equal to 9? And you might already be able to tell that it's not going to, because we're going to get fractions, but let's just see this fully through to see what happens. So how do you square a fraction? Well, multiplying a fraction by itself means that you multiply numerator times numerator and denominator times denominator, right? So you get 25/4. And so now what we're asking is it true that 25/4 plus, so what do we get here? -1 plus 2, that's 1 squared. And this is what we're checking whether that's equal to 9. And so now we have 25/4 plus, so 1 squared is 1. Let's rewrite that in terms of fourths, just so that we can be like extra sure of what happens here. So if we add these two numbers together, we get 29/4. And 29/4 is not equal to 9, right? If it was, then it should be divisible, but 29 is not divisible by 4. And so that tells us that the answer is no. This point does not lie on the circle. So that's what I mean when I talk about the equation of a circle. It means that any point that is on the circle, when you plug it in, you get a true statement. Any point that does not actually lie on the circle, if you plug it in, you will get a false statement. All right, so as I said, the next video will be back to talking about functions. And as always, I really recommend that you look at the worksheet for today, where you'll get more practice with basically all the types of questions that we did in this video. So I'll see you next time.